again, it's a parallel algorithm where we start out with a bunch of random hyperparameters at the start, and then after some time step, the worst parameters, we just cut them off, and then have half of it keep going, and then after another time step, we cut them off again, and then at the end, we only have one set of parameters go all the way to the end. So this will save a lot on computation compared to like random search. But it's still not this is still just a random search in essence. So people have also combined this with other techniques like Bayesian optimization. Okay. Alright, so now I'm going to move into neural architecture search. And I'll talk about the different methods for doing that. So again, neural architecture search, this is like finding the best neural network for your data set. And there are three main components that go into a NAS problem. The first is the search space. So what set of architectures are you searching over? The second is the search strategy. So what algorithm are you using to find the best architecture? And the third one is the evaluation method. So that's like on the last slide. Like, do you train every single architecture to the end, or do you cut some off if they're doing badly at the start? Okay. So the search space. This is actually a really important ingredient to neural architecture search. So first, you need to decide whether you're doing macro search or micro search. So macro search is like you have some data set where you have no idea what could be a good method. You don't even know like if you should use a convolutional layer or like an LSTM or something. So then, so you have no idea. So you want to have like a huge search space. Whereas micro search, you might have a little bit of an idea of what would work well, and you're really trying to eke out like the top 1 or 2, like improved by 1 or 2 more % accuracy. So for macro search, a common technique is called a progressive search. And that's where we start out by learning a smaller neural network. And then once we start to optimize that, we add on some more layers and optimize over that. And then keep progressing, keep adding more layers as the search progresses. So this is a good technique. If we don't even know how big our neural network should be, we can use progressive search and see when it converges, how many layers we need. And then, so for micro search, a really common method is a cell-based search space. So the idea for a cell-based search space is we search over a smaller, like size 10 neural network on the right. Like usually it's like 10 nodes that can each be some operation in a directed acyclic graph. So we're searching over all possible directed acyclic graphs with where the nodes are some operations like convolution or ReLU or something. And then, so this is a pretty small neural net, but then we build a bigger one by stacking all of them on top of each other. And then it's common to add some reduction layers partway through. For example, for image data sets, it's common to add some downsampling every once in a while because that helps. So this is a really nice technique because we're doing the search over a smaller set, but we still get the power of a really big network. The only downside of this approach is that we're injecting our human knowledge. Like we know that this is a pretty good framework, so we're adding our human bias to the search space. So that can be good, but it's also like we won't learn anything like really novel for our problem. Okay. So that's it for search spaces. Now I'm going to get into the actual NAS algorithms. And I'll start with Bayesian optimization. So this can also be used for hyperparameter optimization. It's actually more common for hyperparameter optimization. But I'll just be presenting it in the framework for NAS. And I can talk about how we can also use it for HPR. Okay, so it's a really popular method, and the reason is it's a really efficient way to optimize a really expensive function in a zeroth order way, and that's exactly what deep learning is. Okay, so first we fix some data set, and then we define a search space, like on the previous slide. All right, and then so to be formal, we define a function where the input is a neural architecture, and the output is the accuracy of that neural architecture. And our goal is to optimize this function. Okay, so Bayesian optimization also needs a distance function between different architectures. And we want the distance function, so if two architectures, if the distance is close, we want the difference in accuracy to be pretty close. Okay, and it's pretty common to use some heuristic for this, like look at the architectures. If like the layers are pretty similar and the operations are pretty similar, then we give a small difference, and if they're like widely different, then we give them a large distance. Okay. Okay, so alright, so we want to maximize the function, and the framework is, at the start of the search, we just choose a few architectures at random and then evaluate them. And then after we do that, we start this iterative process where we use the results from the previous architectures to decide on a new architecture to use. Okay, so the key part of Bayesian optimization is how do we do this step? How do we decide what the next architecture is that we choose? Okay. So the idea of Bayesian optimization is to model this using Bayesian statistics. So if we look at the function space of our function f over all possible inputs, we assume that this space is fairly smooth. If it was just jagged and random, then we would have no hope of doing anything. So we assume it's a bit smoother, like the pictures on the right. And formally, we model this as a Gaussian process, and basically that means, like, if you know a Gaussian random variable, it's basically like the function version of that, where we have some function and its deviations look something like random noise. Okay. And then at the start, we don't know which function this could be, but then as we query more and more points, we get a better idea of what our function is. Okay, so say we queried 5 points, then we know exactly what the function is for those points, and we also know, we have a pretty good idea of what it might be close to those points, but then further away we're not so sure yet. So the gray area is like the uncertainty region for these functions. Okay, so now we have a model of we have like a posterior probability over all possible functions, and then now we want to do some exploitation trade-off. So say we have a few architectures that have done really well. So we want to look around that space to try to get other really good architectures. But we also want to occasionally explore, like try completely random architectures in case they do even better. So this is formalized with an acquisition function. So in the top right, say we've drawn 3 architectures so far. So we have a pretty good idea that like this is a pretty good space, but over here we have no idea, and maybe it's much better. So a common acquisition function is expected improvement. This is the expected value of the improvement of the new architecture over the best one we've seen so far. Okay, so if we optimize our acquisition function here, we get this point right here. Okay. So this is Bayesian optimization. Okay, so the next NAS algorithm I'm going to talk about is this is a really popular algorithm in the last couple of years. It's called DARTS, Differentiable Architecture Search. And the reason this is a popular idea is earlier I claimed that most of NAS is zeroth order, but this algorithm actually found a way to make a first order problem. Okay, so they make it into a continuous problem, and that allowed them to do gradient descent, which is more powerful even than Bayesian optimization. Okay, so how do they do this? So at the start, we have some architecture and we have no idea. So in this picture, the edges are actually the operations. So we have no idea what this operation should be. So the idea is let's just put all possible operations there. So say the red line is like a convolution, the green line is like a pooling layer, and the blue one is a ReLU. So we just put all possible operations there, and we add a weight to all of them. So at the start, the weight is 0.33 for all of them. And now that we have a weight, this is actually a continuous number. It can be anything from 0 to 1. So now we can do gradient descent on these weights. So this is exactly what they do. So the algorithm is, we start with a neural network, and we learn the architecture and we learn the parameters and the hyperparameters in parallel, where in every iteration we switch off between doing a gradient step for the parameters and a gradient step for the hyperparameters. And they actually showed, even though this seems like a complicated problem, it actually converges to a pretty good architecture. Okay, and so the benefit of this method is we only have to train a single architecture. So in like Bayesian optimization, we might have to do many iterations of like 100 or 1,000 architectures. But this one, we just train a single architecture. The downside is that so it works well in the micro search setting, but it's not as tested in the macro search setting. So in the original research paper, they had a fairly small search space. Okay, so I'm going to talk about one more NAS algorithm, and this is reinforcement learning. So this is a method where we use a neural network to learn the best neural network. Some crazy idea. So we have some controller recurrent neural network, and the job of the controller is to decide on neural networks to try next. So it spits out a neural network, and then we train that neural network and feed the accuracy back, so that the controller can update its own parameters and become better at predicting other neural networks. Okay, and this is modeled in a reinforcement learning framework. Okay, so this is potentially like a really powerful method because we're using an entire neural network to learn other neural networks. But the downside is that some people say this might be overkill because NAS is in essence an optimization problem. So why do we need to add the entire reinforcement learning framework where you have like a state and transitions and an action? It seems like it might be overkill. Yeah, so I just want to conclude talking about NAS by like giving you an idea of where we are in this field. So there's a huge amount of results just in the last 2 years. There have been hundreds of papers, like a huge explosion of research. And with that comes, sometimes it's like hard to reproduce the results, and sometimes it's hard to compare different algorithms, because everyone's using their own search spaces, their own like pipelines of training methods. So we're getting a better idea of what are good algorithms, but we're really lacking like a big comprehensive study that like fixes all the variables and decides like what methods are the best for what types of problems. There is some recent research in this direction. Yeah, just to give you an idea, so there's actually some results from earlier this year that looked at some recent research and found that just doing random search is already like a pretty good baseline for certain search spaces. So yeah, so there's definitely some progress, but we need to make sure we're doing like a comprehensive, like fair comparison. So now in my last few minutes, I'm going to talk about automated data augmentation. Okay, so data augmentation. This is the idea where, say we have some big image data set where we're trying to learn a neural network. It's really easy for us to overfit our model. Okay, so if we have some really big neural network, it might just be like doing tricks like looking at the individual pixels of each image and classifying based on that, where we really want it to learn like higher, like more general features so that it can generalize. And what people have found is that data augmentation helps this a lot. Okay, so data augmentation is the idea where maybe we can like rotate a picture or like crop it or change the colors a little bit. And if we add all these augmented images to make our data set bigger, then it helps a lot with generalization. Okay, but the downside is that we need domain knowledge in order to do this. So if you think about like some data set of images of numbers, so if we have an image of the number 6, we know that we can crop it or rotate it a little bit and it won't change the label. But if we rotate it 180 degrees, it will change the label. So we're using our domain knowledge. And so then when we go to a new data set, like some big tabular data set where we don't really know what anything means, then it's hard to say like what can we change to where we don't affect the label. So there's been some recent research in how do we automate this process of doing data augmentation. Okay, and I will talk about one of these techniques. It's called a data augmentation generative adversarial network. So the idea here is that this is an algorithm for meta learning. So we have one source data set and a target data set. And the target data set is the one we care about. And the source data set we're allowed to use, and we assume they're related data sets, but different. And so the idea is that we can use the source data set to learn augmentations and then apply those augmentation policies on our target data set. And this is shown to be an effective method. So the way the algorithm works, it uses what's called a generative adversarial network. This is a really popular generative model in deep learning, where if you've seen online those like images of faces of people that don't exist, that's like this algorithm that's generating those images. It's a really powerful generative model. And so if we tweak the loss function of the generative adversarial network, we can get it to, instead of just like trying to reproduce the initial data set, we can get it to learn augmentations of the data set that'll keep the label of the data the same. So this is the architecture for the data augmentation GAN, and then it turns out this is very effective. So on the right is some images that we at RealityEngines have used when we're like playing around on fruit data sets. So the first column are the real images, and the next 3 columns are generated using this technique. So, and this was for the target data set, so it wasn't even trained on these classes. Okay, so this is a really powerful technique for automated data augmentation. Okay, so now to conclude, so I talked about automated machine learning. This is the idea of automating all parts of the machine learning pipeline. And then HPO and NAS are 2 of the biggest subsets of automated machine learning. And here are some of the most popular algorithms. Okay, so thank you.